Hello, welcome to Math 1324. This is Chapter 10, Section 3, Example 7. In this example, we want to find any horizontal and vertical asymptotes and any holes that may exist for the rational function. Draw the graph of the function, including any x and y intercepts. Okay, so here's the thing. Looking at this, I'm gonna go ahead and find the domain. So finding the domain, we take the denominator. Again, this wasn't asked for, but I want to go ahead and do it. It's wherever the original question's denominator is not equal to 0. So the original question's denominator is x plus 3. So that means that x is not equal to negative 3. That means that the domain for this is negative infinity to negative 3 union negative 3 to infinity. Excellent. There you go. That's the domain. I just wanted to get that out there. Now, what we need to look at now is finding horizontal and vertical asymptotes. But before we do that, I want to look for any holes in the graph. To look for holes, holes exist where factors cancel. Okay, so what we need to do is look at the function, but instead of writing it as it is, let's write it in factored form in both the numerator and denominator. Okay, so the numerator is x squared plus 7x plus 12. The factorization is x plus 3, x plus 4. Look at the denominator, it's x plus 3, so it just remains as x plus 3. And this is important. X plus 3, x plus 4, each one of these is one big factor. But notice that that's also one big factor as well. In other words, that x plus 3 cancels. And this simplifies to just y equals x plus 4. And yes, y equals x plus 4 is a line. But what's important about this is that it's not really a line. It will look like a line when you graph it, but it's really not. And the reason why is because this is our function actually. In actuality, our function is x squared plus 7x plus 12 all over x plus 3, and our domain is this. It's the reason I'm looking at the domain. This looks like it has a domain of negative infinity to infinity, but it doesn't. This is actually the domain that we need. The reason that we have that is because the denominator can't equal 0, but it's still not going to be a vertical asymptote. And the reason I say that is that x plus 3 canceled. And so as a result, there is a hole where the denominator, or in other words, the factor, is equal to 0. Subtract the 3, so x equals negative 3. There's a hole at x equals negative 3. And if you want the coordinate, and we probably do, we're going to take this x, plug it into our simplified form of the line, or the simplified form of the function. That means that y is going to be equal to negative 3 plus 4, which is 1. So the coordinate, there is a hole at negative 3, positive 1. Awesome. Good deal. So that's a hole. Now let's look for any vertical asymptotes. But remember, vertical asymptotes can only be found from the simplified form. And the simplified form is right here, y equals x plus 4. What's the denominator? The denominator is 1. It's understood to be 1. And so take that denominator, set it equal to 0. Is 1 ever equal to 0? No. So that tells me that there is no vertical asymptote. So it's possible not even to have a vertical asymptote. Even beyond getting rid of denominators, we don't always have vertical asymptotes. For example, if we had x squared plus 1 in the denominator, that's never equal to 0. Because you get imaginary numbers, aka x squared plus 1, the lowest that can ever be in the real numbers is 1. So as a result, there would be no vertical asymptote there. So it really does depend on the function. There's a lot of weird things that can happen with rational functions. For the horizontal asymptote, If we look at n here, n is 1, d is 0. So the relationship between 1 and 0, what is it, mathematically speaking? It means that the numerator degree is greater than the denominator degree. In other words, there is no horizontal asymptote. And even beyond that, that tells me that there is a slant asymptote. And the slant asymptote is actually y equals x plus 4. And that's pretty much it. I'm not sure if my math lab asks for a slant asymptote or not, but there you go. All right. What does it even mean to have a slant asymptote? Well, the slant asymptotes, aka oblique asymptotes, tell us what the function is doing as x gets really, really large or really, really, really small. And in this case, it's exactly what the function is doing. It's not an approximation, it's exact, simply because the simplified form is actually y equals x plus 4. If it wasn't y equals x plus 4, if it was something like this, say sidebar here, if we had something like x squared plus 3x, let's say x cubed plus 3x plus 4 all over x plus 1, the oblique asymptote, it would be a little bit more difficult to find because you'd actually have to do this division and then ignore any remainder. And so whatever you got when you did the division, but ignoring the remainder, that would be your oblique asymptote. So that's what you would do. You would actually have to do the division long ways, and well, in this case, you could do synthetic division. But if it was say, whatever, do the division, ignore the remainder, and then the answer is your oblique asymptote. Awesome. And then, of course, x-intercepts would occur where your simplified form equals 0. In other words, x equals negative 4. And then your y-intercept occurs where x is 0. In other words, y equals 4. Alrighty. Well, there is all of the work for this particular question. And I'm going to go to the calculator and show you, well, what this is going to look like. I'll see you there. Welcome back to the calculator. I have already reset y1, and I'm going to go ahead and change y2 back to its original. Alright, good deal. So, let's go ahead and type in on y1, first of all, alpha y equals enter, and we're going to do the original question of x squared plus 7x plus 12 all over x plus 3. And then zoom 6 for the standard window. Awesome, it looks like a line. And that's true, it does. But Pearson's not going to have that, or it might have this as an option, but that would actually be wrong. So we have to be very careful, because if you remember, there is a hole in the graph here. The domain is not all real numbers. And to actually see that, we're going to have to get really, 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 really close on the calculator. This is why actually knowing how to find holes in the graph is actually very important for us. So the hole occurs at negative 3, 1. So negative 3, positive 1. It's somewhere right there. But that means I'm going to have to zoom in really close. So if I go to window, my minimum, I'm going to make that negative 3.001. And for the maximum, I'm going to make that negative 2.999. For the y minimum, I'm going to make that 0.999. The y maximum, I'm going to make that 1.001. So if you notice what I'm doing is I'm making the x min and x max and y min, y max be pretty close to what the coordinate is. It's negative 3, 1. So negative 3.001 to negative 2.999. And the y min 0.999 to 1.001. And then I'm going to graph this. Awesome. And out of all this, notice that there's just barely nothing written there. Still, it's very hard to see that. And there is actually a hole in the graph there. That's how your calculator does this. It's the reason the calculator is not exactly the best for this. But what you'll see in MyMathLab is an open circle there. Okay, and the reason I say that is so that you can understand what's happening. An open circle will indicate that there is a hole in the graph. And in fact, what you'll actually see is something like this with a hole in the graph right here at negative 3, 1. Alrighty, well, I believe that's it. In fact, I believe that's it for, well, this entire section. I know you're so disappointed to hear that. Anyway, I will go ahead and see you in the next section.